In this video segment, we will be presenting how we deploy the US D96 and the US D99 depth integrating bag samplers. Also, we will clarify how our large river teams use the data previously collected by the ADCP flow measurement to determine equal discharge increment sampling points across the Mississippi River. Before sample collection begins, we determine which sampler we will use from the hydrologic conditions we expect at the site, like the approximate maximum depth and estimated velocity in each transect. This table summarizes the bag samplers we routinely use and their approved and tested limitations. Although there are some overlapping velocity zones and depths, the main concern would be using the proper sampler for each condition that would not approach its limitations of velocity and/or depth. If this were to occur, the sampler suspension cable would likely have a drag angle that would require a depth correction to be applied. We routinely use the 3-liter bag in the D99 sampler during increased flows and mid-depths like 70 to 80 feet to utilize the increased weight of the sampler and therefore reducing the drag angle. Next, we would select the type and size of nozzle we will be using. There are two types of materials that the USGS uses to make nozzles. Teflon, PTFE, which we utilize solely for our water quality data collection due to the material's non-stick attribute. Deldrin, or POM, is a plastic type of material. Either of these nozzle materials will be suitable for sediment collection, although the TFE is very expensive and provides no notable advantage over plastic in sediment sampling. The same goes for the sample collection bag material, type and size. The USGS uses TFE bags for water quality collections and plastic bags for our sediment data collection. So these are two 6-liter bags, they're very large bags, for use in the D99. One is Teflon, you can see it's more transparent, and then this one is more translucent. This is the plastic bag. So these are the sizes of the 6-liter bags that will only be and only can be used in the D99 sampler. For comparison, this is a D96 bag or a 3-liter bag. Now, the 3-liter bag can be used in the 99 as well, but the 99 6-liter bag cannot fit inside of the D96. So these are two Teflon bags. And if you wanted to look at a poly bag, a plastic bag, in the 3-liter size, you can see the difference in the materials. So these are the two type holders that we use. This is a D96 nozzle holder. This would be a D96 nozzle with the short threads. This is another D96 nozzle in the Teflon material. And this would just screw into this nozzle like this. The D99 nozzle holder is just a little bit taller, but the same. It's got a thicker base. The nozzle for a 99 has a gap here, so we can tell which nozzle fits in which holder, and then it will just screw into the base like this. The nozzles are the main operational aspect of the sampler. From these federal interagency sedimentation project blueprints, you can see the specific dimensions and tolerances from 3 views. The nozzle opening diameter and the taper ream dimensions are of particular importance. The taper ream was engineered to allow the flow of the water into the collection bag at the same rate as the stream velocity, with no resistance. It is highly recommended that all sample nozzles be inspected for damage before each use. The PTFE and plastic materials are soft and can be deformed from dropping on or striking hard objects. Here are a few examples of deformed nozzles that should be discarded. These are good examples of some nozzles that we've taken out of circulation. As you can look at this one, it's a little deformed there, but if you look at it closely, it's really out of round, probably from striking something coming up out of the water. Could have dropped it on the ground. Here's another one that really has a bad deformity on it. These nozzles are not repairable. They cannot be melted down. Here's another one that you can really see the abrasion on and the deformity it has. This would really affect the sample efficiency and the dynamics of the water flowing through the nozzle. The last nozzle I want to show you is a 1/8 inch nozzle that was developed years ago, but then the flow efficiencies of this nozzle weren't up to par, and so this nozzle was discontinued many years ago. As you can tell, it has a very, very small opening, and tests done with the USGS did not show a positive result for the efficiencies of this size nozzle. So that's just a couple examples there of some nozzles that we will do away with. Like I said, they cannot be repaired. This material cannot be melted down and reused, and so we will have to discard these. For large river sampling, we utilize the equal discharge increment, EDI method of sampling instead of the equal width increment method for several reasons. One, large river crews have ADCP units available to compute flow and measure velocity. Two, crews can save time by doing less sample collection points across the river. USGS standards state if using the EWI method, a minimum of 10 collection points across the channel is recommended. If using the EDI method of collection, those points of collection are flow weighted and therefore can be between 4 and 9 points across the channel. At large river sites, we typically set 5 EDI transects for collection points. Bottles collected using the EDI method may be analyzed individually for comparison or composited when equal volumes of sample are collected from each vertical. However, both methods will yield the same results if properly used. Once the proper sampler and appropriate nozzle for the current depth and velocity has been selected, we need to determine the EDI collection points across the river. We can accomplish this task from a few different techniques. 1. Use the output file from the QREV software, which gives us an average of several ensembles left and right of that point for depth and stream mean velocities at each section. This output will also produce the latitude and longitude of those points for the cross section and can output a map also. 2. Manually compute the EDI midsection points from the ADCP measurement. The crew uses the total flow measured to hand compute the center of 5 equal discharge sections. So from our measurement, we hand computed what our 10, 30, 50, 70, and 90% EDI sections would be. So these are our stations and our waypoints that we've set. These are our individual discharges. So our total discharge was a little over 1 million. So we hand computed this, and we're going to use live readings. So we've got the Doppler pinging, we've got it recording, so we'll have all this information if we want to go back and look at it. So we've already set our waypoints. Al, can you zoom out a little bit so we can see how our waypoints over the many years have lined up? We've got a nice accumulation in how they line up on our 10%, our 30, our 50%, 70, and 90 percentiles. And those are taken in between 20% sections. So we're doing 5 stations, dividing the river into equal discharge increments, and then sampling in the middle of those increments to complete our equal discharge increment suspended sediment sample. After this ADCP pass is completed and we have our sampling points marked, we can return to those waypoints and collect our samples. Another advantage to setting marked waypoints for sampling would be river traffic. We routinely have various towboats pushing any number of barges upstream and downstream of our sampling sections. Sometimes these can be as many as 42 barges tied together, 6 barges wide and 7 barges in length, which is nearly 700 feet long and 240 feet wide. On the lowermost sections of the Mississippi River, we also have large oil tanker ships. We always yield to these vessels and keep a safe distance from their draft and prop wash, which can be very intense and can cause small boats to capsize. In saying this, by setting our sampling waypoints, if we had to move due to river traffic, we can always return to any waypoint and finish our sampling routine after the vessel has passed. We're always cautious and let the barge traffic go by because they've got the right of way. So what we're going to do is we're going to hang out here for just a few minutes until this larger barge navigates down the channel, and he will eventually pass through the bridge at Vicksburg. And so at this section on the Mississippi River, this hairpin turn is one of the most dangerous turns on the river. And at flood stage and even higher, these large barges that can be pushing up to 47 barges at a time. They are pure professionals, and we let them have the whole river to themselves. So we don't want to get in their way, create any more tension on them than we need to. So our measurement can wait. So we're going to sit here and pause for just a few minutes and let him pass and do his job, and then we'll complete our second pass. If we use the QREV software, we can enter the latitude and longitude into our Garmin map screen to set our sampling waypoints. The sample data points generated from QREV is a great starting point to have a good idea of the velocities and depths. But we usually adjust those numbers by referring to the live Doppler readings once we are on that waypoint. Large river instantaneous velocities can vary depending on the channel's geomorphology and other controlling factors. Discharge on the lower Mississippi River has been documented to have some pulses in velocity during the higher flows due to several controlling factors, including distributaries, restrictions due to bridges, and other flood control structures. We routinely see the velocities at a sample location fluctuate plus or minus 1 to 2 feet during these conditions. Next, our boat captain maneuvers to the first waypoint to collect one of 5 verticals for our EDI sample. At this point, the boat is held in a stationary position and pointed into the flow. Once the captain signals we are on target and we are stationary, we read the live depth and velocity from the ADCP. We compare those to the rear-mounted sonars, which are mounted closer to where the sampler will be deployed. See the differences here. So this is side scan. This is our GPS map. You can see our sampling points that we're going to go to. So I use all of this kind of a reference. When the boat's steady, you'll see this boat symbol turn to a circle, and I can look at the speed here. That means just like now. And I can see that we're steady, and he's holding the boat as steady as he can. So this is actually a live view. It's a little bit blurrier, but when the sampler goes down, you'll be able to see the sampler log down there on the bottom. This is the boat, and this is looking like 40, 50 foot. Probably our boat is like 26 foot. So our boat is here. This is the transducer in the back of the boat. It's shining to the back of the boat and about 50 foot from the back of the boat up. So our boat is like right in here. And so you'll see the sampler come down in this zone. As you can see with this recording, the live Doppler readings are changing plus or minus a half a foot or more. Usually we will stay stationary on a point for a moment and use the best mean velocities possible. These numbers can be close to the velocities projected by the QREV software, but they can also vary. We prefer to use the live ADCP readings because the river's depth and velocities are constantly fluctuating. We have recently acquired the latest sonar technology from Garmin Electronics with a panoptic transducer. This technology is proving to be the best advance we have added to our sampling capabilities as far as monitoring the bed forms and position of the sampler during deployment. With this unit, we can view the sampler in real time as it travels through the water column. Not only can we view the sampler position in real time, but we can see extreme details like the air bubbles leaving the cavity of the sampler and the position of the suspension cable in the vertical. During deployment of the sampler, we can monitor the bed form's position and movement in real time in association to our projected vertical sampling section. This is a real-time view we can utilize to help avoid unwanted bottom contact and dangerous snags. Once we have the best mean live velocity and depth from the ADCP, we can compute our sampler transit rate by using a table which comes with every sampler. This table allows us to use the mean stream velocity and total depth to compute filling rates. We have revised this table to allow us to collect only 80% of the maximum volume of 3 liters so that we will not approach overfilling the bag. The way this works is we take the live depth, multiply that by 2 for the descending and ascending path in the vertical, and divide that by the filling time in seconds from the chart utilizing the mean stream velocity. This gives us the transit rate to deploy the sampler in feet per second and collect 80% of 3 liters. Once we have the transit rate computed, we begin to deploy our sampler. Go. We usually lower the sampler multiple times at each EDI point to collect water quality and sediment data. On the first deployment, we collect our suspended sediment sample only. First, we measured that bag's volume by either weight or by a graduated cylinder.
The problem with using a graduated cylinder is we have to discard this because there's no real way to get all of the sand out of there. So use a graduated cylinder. It's good for measuring efficiencies, but this water has to be discarded. So that's why we went to the scale method, and we dump each sample in the individual gallon jugs. We can take those jugs back to the lab and measure them on a better scale and get more accurate weights. We'll tear the bottles. We can use those weights, volumes, one-to-one comparison, to update our efficiencies to see if it helps or lowers the efficiencies.
Got my pre-labeled bottle. I have to take the sample. And we're going to shake it up 3 times to get all the sand, all the fine sand out, so that the sample that we send to the lab has all the sediment that we collect. So it won't get stuck in the bag and not end up in the sample. I don't see any fine sand. It looks like we've got all the sediment from this sample, and I'm just going to make sure the lid is tight so that when it gets to the lab it doesn't evaporate out. Concentrate.
So in looking at some of our EDI samples, you can see that they're basically about the same volume, and that's what we're looking for. So we got 5 of these, and so that's what we'll end up sending, and we can have those composited at the lab, and we can do our sand fine analysis on them, our sand silt splits, concentrations, and we'll carry those down there by truck to our Baton Rouge office.
During that collection, we time the deployment and record the efficiency for that sample from the following formula. We have this formula set up in an Excel file that will compute the efficiency by entering all of the numbers required. We have compared measuring the sample volume during collection by using a 4,000 gram portable scale on the boat to weighing the sample in the lab after collection. Those numbers usually check very well. The data needed to compute efficiency: 1. Nozzle size, 2. Mean stream velocity at the point, 3. Sampler submersion time in seconds, and 4. Volume of the sample collected. USGS methods state that transit rates can and should be adjusted for each section when using the EDI method. This will allow the collection volume from each subsampled section to be very similar. The USGS methods also state that nozzle sizes should not be changed between verticals.
First, we determined the mean stream velocity at the sampling point using the ADCP. Then we timed the submersion of the sampler with a stopwatch and record that on an Excel field form. After we collect the sample, we measure the water volume by weight with a scale. Although depending on the sediment concentration and sample volume, this method may not be the best technique to determine the sample volume in every case. Sometimes this can be challenging when we have rough river conditions like heavy barge traffic and/or waves from high winds. If we're unable to measure the sample by weight due to boat movement, we can measure the volume with a large graduated cylinder. Although if we use this method, the sample will need to be discarded and then resampled due to the chances of sediment losses from pouring from one container to another. Another method we have used is measuring the sample volume back at our office using a scale and subtracting the tare weight of the bottle and lid and recording the weight sample in grams. This comparison has proven that weighing the sample on the boat can result in a true representation of volume. This allows us to keep the sample for analysis as we pour it directly into its own container on board the boat. We then record the sample depth and average water temperature and enter those numbers into the field form. Once we have all these measurements entered in the form, we can see the sample's computed intake efficiency. If this number is acceptable, we keep the sample and move on to our subsequent waypoint to collect the next sample. If we compute an unacceptable efficiency, we pour out that sample, reevaluate our mean stream velocity from the live ADCP readings, check our nozzles and sizes and river depth, and recalculate our transit rate, and then we resample. It's not uncommon to see some incorrect efficiency computations due to selecting incorrect instantaneous stream velocity, which is the dependent variable in the equation.
In these next video segments, you can view crews using the D99 during some higher flows, usually with velocities around 7 feet per second, and later using the same method using a much lighter 130-pound D96 to collect samples at some lower velocities.
So we're inspecting the nozzle to make sure it's in good shape. We don't have any nicks or where it's deformed. And this one looks good. So we're using poly bags for sediment. This is a 3-liter bag today. 3/16 nozzle. We're going to use the rates for 3/16 nozzle, and we should be expecting somewhere around 2,300 to 2,500 milliliters.
Are we on point?
Yes.
All right, we're going to deploy.
Go ahead, we're ready.
They're ready.
All right.
Give me a depth.
Depth is 50 feet.
Okay.
Yeah.
Water speed's 5.
5. So give me a transit rate.
Transit rate will be 1.1.
1.1. Say when you're ready.
Ready.
Ready. Go to 50.
Go into 50. When you mark, sit. Go. Now I'm monitoring the depth here on the dial, the true depth of the sampler. I'm also watching it on the live scope. I'm seeing we got a circle here, so I know the boat's steady.
Go to 48.
Go to 48.
We're at 10 feet.
Go to 48.
Going to 48. Depth is changing. We've got some little small dunes right here. I'm at 20 feet going down now.
Yeah, 48 still good.
Go to 48?
48.
I'm at 40. 2, 3, 4, 5, 6, 7, 8. Coming up.
Perfect.
See the trace of the sampler right here from this side scan. We were just off the bottom. I can see the sampler coming up in the live scope. Looks good. I like to use these because you can see any debris, sunken objects that could be on the bottom of this large river, which could be a hazard. So it takes constant communication. So I'm at 15 feet coming up. We're 5 by 5, 15 feet. I'm at 5, 3, 2, 1, out. Water you see coming out of the cavity is just the open cavity. So that looks like about 2,300 mils. And so, Claire, I'll let you take it. So we always wear water quality gloves, nitrile gloves when we're sampling water quality to protect our sample. During sediment, it's not that important, but it's recommended that we wear gloves not to protect the sediment sample because our hands are mostly clean, but we wear gloves on this size river and most rivers, even with sampling for sediment, because we're protecting ourselves from the water. There could be pathogens or bacteria, so it's just a protection for us. So this is a C-style clamp holder for our samplers. The cable just goes through and then it's got this pin that goes down into it, and increase weight, the heavier the weight, the tighter it gets on the cable. So it's much easier than using a B connector or one of the other connectors where the cable has to intertwine through there. At times we have to cut off frayed cable and shorten the cable up. So we can do this in a matter of minutes instead of an hour.
Yeah.
48 at 1.3.
Yeah.
So tomorrow we're going to go to our Baton Rouge office and we'll be filming there with Lane Simmons on his boat. We'll be looking at using a point sample that he uses routinely on a lot of sites that we work with the Corps of Engineers in cooperation with them. They're our partners on a lot of sites on the lower Mississippi River. And so he'll be demonstrating how he uses the P6-200. His boat's a little different with the setup. He's got a newer boat, and it's been designed where they can sample off the front of the boat. The main reason for that is because he takes bed sediment with bed sediment samplers. So he's actually contacting the bottom pretty hard to get that sediment scooped up in that bed sediment sampler. He uses a BM54, which works really well. So that concludes us here today. And thank you for watching, and we'll see you tomorrow in Baton Rouge.